Have you ever watched a robotic arm elegantly sweep through an arc, or a drone effortlessly pivot in mid-air, and wondered how engineers precisely measure and control such intricate rotational movements? Robotic angular velocity, which describes how fast a robot or its joints rotate, is primarily defined by units of radians per second. This is the standard scientific unit, though degrees per second and revolutions per minute are also commonly used, especially in practical applications and motor specifications. These units provide the essential language for understanding a robot's speed of rotation. The fundamental reason for using these units lies in the nature of rotational motion. Angular velocity is derived from angular displacement, which is the change in angle of a rotating body, divided by the time it takes for that change to occur. Radians, as a unit of angle, are intrinsically linked to the geometry of circles and are the natural choice in mathematical and scientific contexts because they directly relate arc length to radius without needing conversion factors. 1 radian is the angle subtended at the center of a circle by an arc that is equal in length to the radius. This pure mathematical relationship makes radians per second the preferred unit for calculations in robot kinematics and dynamics. For engineers and roboticists, understanding these units means they can accurately specify motor speeds, design control algorithms, and predict a robot's movement. For example, if a robotic joint needs to rotate a certain number of degrees in a specific time, knowing the angular velocity in degrees per second is directly useful. When integrating these movements into a larger system, converting between radians per second and degrees per second, or even revolutions per minute, becomes a routine but critical step to ensure consistency across different components and control systems. This ensures the robot moves precisely as intended. A fascinating detail in advanced robotics is how angular velocity plays a crucial role in the Jacobian matrix, a mathematical tool that relates joint velocities to end effector velocities. The angular velocity components of the end effector are expressed in radians per second, and this matrix helps roboticists translate desired spatial movements into the required individual joint rotations, highlighting the deep mathematical underpinnings of robot control. Ultimately, a clear grasp of these angular velocity units empowers roboticists to design, program, and control robots with confidence, ensuring smooth, predictable, and efficient rotational movements. It transforms complex mechanical actions into quantifiable, controllable parameters, laying the groundwork for precise and intelligent robotic operation.
If you love robotics, like, subscribe, and keep building with us.